Hello again. This is Math 2115 coming to you from the College of DuPage. The title of this lecture is Solving Recursive Equations by Iteration and Induction. Please be an active learner while watching these videos. The most basic method for finding an explicit formula for a recursively defined sequence is iteration. Iteration works as follows. Given a sequence, A0, A1, A2, ... keeping on going, defined by a recurrence relation and an initial conditions, you start from the initial conditions and calculate successive terms in the sequence until you see a pattern developing. At that point, you guess an explicit formula, and you can seek to prove that explicit formula by induction. So let's look at an example of finding an explicit formula. So suppose A0, A1, A2 be the sequence defined recursively as follows. For every integer k greater than or equal to 1, ak is equal to ak minus 1 plus 2, and the initial condition, A0 is equal to 1. And we're to use iteration to guess an explicit formula for this sequence. Okay, now first of all, let's start by recalling that if we say ak is equal to ak minus 1 plus 2 for every integer k greater than or equal to 1, that means a blank is equal to a blank minus 1 plus 2 because the k is a dummy variable. So in particular, we can say that a1 is equal to a0 plus 2, a2 is equal to a1 plus 2, and a3 is equal to a2 plus 2, and so forth. Now, if we use the initial condition to begin a process of successive substitutions into these equations, not just of numbers, but of numerical expressions. The reason for using numerical expressions rather than numbers is that in these problems you are seeking a numerical pattern that underlies a general formula. The secret of success is to leave most of the arithmetic undone. However, you do need to eliminate parentheses as you go from one step to the other, or otherwise you'll end up with a bewildering large nest of parentheses. Also, it's nearly always helpful to use shorthand notation for regrouping additions, subtractions, and multiplications of numbers that repeat. For example, if you had 5 times 2, you would write that instead of 2 added to itself 5 times, and if you had 2 multiplied times itself 5 times, you write 2 to the 5th. Now notice that you don't lose any information when you do these shorthands. So here's how the process would work for this sequence. So A0 is 1, and then we substitute that in the next one. That is 1 plus 2. We substitute that into the next one for A1. It's 1 plus 2 plus 2, but then we write it this way without the parentheses, 1 plus 2 plus 2. We substitute that into the third one, and we get 1 plus 2 plus 2, and then the fourth one we do again a substitution, and we get 1 plus 2 plus 2 plus 2. Now it appears useful to use the shorthand k times 2 instead of 2 plus 2 plus 2k times. And when we do so, starting from A0, we see that we have this, and this. Now, if you look at this pattern, you notice that the number 4, for example, appears here, the number 3 appears here, the number 5 appears over here, and so on and so forth. So it's reasonable for you to guess that an is equal to 1 plus n times 2, and we would usually write that as 1 plus 2n for every integer n. So now this is just a guess, but to prove this we could use math induction, and later in this section we'll show you how to do this, not necessarily on this problem, but on a different problem. So a sequence like the one that we just covered, in which each term equals the previous term plus a fixed constant, is called an arithmetic. It's not arithmetic, it's arithmetic sequence. In the equations to the end of this section, you're asked to show that the nth term of an arithmetic sequence always equals the initial value plus n times the fixed constant. In fact, you're proving that this definition holds. In fact, you're proving that this theorem holds. So if this is an arithmetic sequence, if and only if, This is the definition. The next term is the previous term plus a fixed constant for all k greater than or equal to 1. Then you can also say that a n is equal to a0 plus d times n. And in the previous example, that certainly holds. There are other examples of these kind of sequences. Under the force of gravity, an object falling in a vacuum falls about 9.8 meters per second faster each second, and sometimes we call that meter per second, or meters per second squared, than it fell in the previous second. So then we call the acceleration meters per second squared. Thus, neglecting air resistance, a skydiver's speed upon leaving an airplane is approximately 9.8 meters per second 1 second after departure, 19.6 after 2 seconds, and so forth. If the air resistance is neglected, how fast would the skydiver be falling 60 seconds after leaving the plane? Well, if we let S sub n be the skydiver's speed in meters per second in seconds after exiting the plane, and assume there's no air resistance, then S0 is the initial speed. And since the driver will travel 9.8 seconds each time, you see we do get this arithmetic sequence for every integer k greater than or equal to 1. So it follows that this has a fixed constant, which is this, and then so we can use the results of the previous analysis to suggest that the speed at 60 seconds after jumping out would be 588 meters per second. Now that's over a half a kilometer per second, or over a third of a mile per second. That's very fast for a human. Now fortunately there is air resistance and it really doesn't get quite this fast. We're going to turn our attention now to what is known as a geometric sequence. So we let R be a fixed non-zero constant, and suppose that the sequence A0, A1, A2, and so on and so forth is defined recursively as AK is equal to R, AK minus 1 for each integer k bigger than or equal to 1, and A0 is equal to the fixed number A. So use iteration to guess an explicit formula. Well, we just start plugging in and see what happens. So A0 is A, but then we plug A0 into the next piece to find out what is A1. We get it as RA. Here we get R times RA, and then we get R times R squared A, and so on and so forth. So from this, if you looked at this pattern, you would quickly guess that AN is equal to R to the n times A, or A times R to the n, for an arbitrary integer n greater than or equal to 0. And again, this could be proven by induction as well. Now such a sequence is called a geometric sequence if and only if there's a constant r, such that the kth term is found by multiplying r times the k minus first term for each integer k greater than or equal to 1. And it follows, if you work through this, that an, and again you might be someday asked to prove this by induction, is equal to a0 times r to the n for each integer n greater than or equal to 0. So again, we found an explicit formula. Now here's an example of a geometric sequence in a real-life application. So if a bank pays interest at a rate of 4% per year, compound annually, and A sub n denotes the amount in the account at the end of year n, then AK is equal to 1.4 times AK minus 1 for each integer k greater than or equal to 1. Now if you assume that no deposits or withdrawals happened during the year, and suppose the initial amount was $100,000, and no additional deposits or withdrawals were made, how much would this be worth at the end of 21 years? And how many years would it take to be worth $1 million? Okay, well, here's the sequence. Capital A0, A1, A2, all the way up, and this is a geometric series. That's the initial value, and the constant multiple is this. So we know from the previous discussion that A sub n is equal to 1,000 times 1.04 raised to the nth power. Now after 21 years, we just will plug 21 in there, and we'll find out that this is the amount of money that is in the account. To answer the second question, how many years will it take to be worth $1 million? Well, you see the other side is going to be $1 million, the A. So A is going to be $1 million. It's 100,000 times, but then the variable is up here as t. This is 1.04 t. Now you divide both sides by 100,000, you get this, and then you take natural logarithms of both sides. So this is the natural logarithm of 10, it's the natural logarithm of 1.04 to the tth power. But there's a property of logarithms that says that t can come down in front. This is a property of logarithms. And so you can solve by dividing both sides by ln of 1.04, and you get that it will be approximately 58.7 years, or almost 59 years, but you would reach $1 million if you could make that deposit. Now, an important property of a geometric sequence with constant multiplier greater than 1 is that it grows very rapidly. And if we're just talking about tens, it's 1, 10, 10 squared, 10 cubed, and so on, up to 10 to the 9th. I am going to recommend that you guys watch a video called The Powers of 10 that illustrates this, actually both in terms of positive numbers and negative numbers as the exponents. But you get up to 1 billion really quite quickly. And here's a table that talks about some of the things that happen. 10 to the 7th is the number of seconds in a year. And you have all of these things. You see that 10 to the 17th is the age of the universe in seconds, according to one-third theory. This is the number of seconds you need to process all possible positions of checker games, even if they're executed at a rate of 1 per billionth of a second. This is the number of atoms that are in the universe, and this number is the number of seconds to process all possible positions of a chess game. Now, it turns out that this is a number that is bigger than a Google, and none of these were bigger than a Google, and yes, the Google was the big number that the founders of the Google Corporation were thinking about when they named their company. They spelled it differently, though. I think they made a mistake. They wanted it to be G-O-O-G-O-L, that Google. So I will recommend you watching a Powers 10 video. It's 10 minutes, but it will be certainly not the worst 10 minutes of your life. It's actually a very good video. Using formulas to simplify solutions obtained by a iteration. There are formulas that we've derived previously. In fact, we did these by induction earlier in the course. This is the sum of a geometric series. So if you sum from 1 up to n, 1 plus r squared all the way up to rn, you get this number. And if you add up the first n integers, 1 plus 2 plus 3 all the way up to n, you get n times n plus 1 all over 2. We did those things by induction, and sometimes those are useful, and in fact we're going to use those yet again during this lecture. Okay, now it's time for us to talk about a very famous puzzle and discrete math problem, actually, called the Tower of Hanoi. So Lucas, who is a famous mathematician, French, invented a puzzle he called the Tower of Hanoi. And it consists of 8 discs of wood with holes in their centers, and were piled in order in decreasing size on one pole in a row of 3. So it looked like this. Now actually in his little game, he did not have 64. He had only 8, and then he had 2 poles like this, but they were stacked in that manner. And a facsimile of the cover of the box is shown in the figure. And those who played the game were supposed to move all the discs one by one from one pole to another, but they were not allowed to place a larger disc on top of a smaller one. And directions in the puzzle claimed it was based on an old Indian legend. And this is the legend that was in his game. On the steps of the altar in the temple of Benares, for many, many years, Brahmins have been moving a tower of 64 golden discs from one pole to another, one by one, never placing a larger one on top of a smaller. When all the discs have been transferred, the tower and the Brahmins themselves will fall, and it will be at the end of the world. The puzzle offered a prize of 10,000 francs, about 45,000 US, to anyone who could move a tower of 64 discs by hand while following the rules of the game. And we'll talk about what that is. Now, assuming that you transferred all the discs as efficiently as possible, how many moves would be required to do that? Okay. Now you have to start thinking about this. Then we have 64 golden discs that are like this. So here is a solution. An elegant and efficient way to solve this problem is to think recursively. Suppose that you, somehow or another, had found the most efficient way possible to transfer a tower of k-1 disc, one by one, from one pole to another, obeying the restrictions that you never place a larger disc on top of a smaller one. What is the most efficient way to transfer a tower of k discs from one pole to another? And the answer is going to be sketched out when we look at this. And in the figure that we're going to look at in a moment, pole A is the initial pole and pole C is the target pole. Now, here is a way to do it. Transfer the top k-1 disc from pole A to pole B. Not all of them, but the top k-1. And if k is greater than 2, this will require a number of moves of individual discs among the three poles. But the point of thinking recursively is not to get caught up in imagining the details of how these moves will occur. And then, step 2 is move the bottom disc from pole A to pole C. And then you transfer the top k-1 from pole B to pole C. And again, if k is greater than 2, execution of this step will require more than one move. Let's look at the picture now and see what we're doing. So, to see this, the sequence of moves is most efficient. Observe that to move the bottom stack of k disc from one pole to the other, you must first move the top k-1 disc to a third pole to get them out of the way. That's what's happening here. So you start with this and you move the first k-1 disc. To transfer them off the bottom disc, to free the bottom disc so it can be moved to another, to transfer them back on top of the bottom disc after the bottom disc has been moved to pole C. So you see you're taking the k-1, then you're here, then you're taking this biggest one and putting on the bottom, then you have this. Okay. If the bottom disc were not moved directly from pole A to pole C, and it were moved to pole B first, at least 2 additional transfers on the top of k-1 disc would be necessary. One to move from pole A to pole C, so the bottom disc could be moved from pole A to pole B, and another to move them off pole C, so that the bottom disc could be moved onto pole C. You want to think about these words probably more deeply than I'm saying them. Spend a little bit of time with this. This would increase the total number of moves and result in a less efficient transfer. That's kind of the proof that this is the most efficient transfer. Hence, the minimum sequence of moves must include going from the initial position to position B, here's position B, to position C, and then to position D eventually. So, it follows then that the minimum sequence of moves must include going from the initial position A to B to C to D, and it follows that the minimum number of moves needed to transfer a tower of k discs from pole A to pole C is the minimum number of moves needed to go from position A to position B, plus the minimum number of moves needed to go from position B to position C, plus the minimum number of moves needed to go from position C to position D. Okay, so let's let n greater than or equal to 1 and let mn equal the number of moves needed to transfer a tower of n discs from one pole to the other. Now notice that this is independent of the labeling of poles. It takes the same minimum number of moves to transfer n discs from pole A to pole C as to transfer n discs from pole A to pole B, for example. Also, the values of mn are independent of the number of larger discs that may lie below the top end, provided these remain stationary while the top end are moved. Because the discs on the bottom are all larger than the ones on the top disc can be removed from the pole to pole as though the bottom disk were not present. Going from position A to B requires M minus K moves. So this is from A to B, and going to C just requires one more move, but then going to position C to position D requires M minus K again. So you see MK is equal to, we got MK minus 1 and MK minus 1, so this is 2 MK minus 1 plus 1 for every integer K greater than or equal to 2. Now the initial condition or base of this recursion is found using the definition of the sequence. You see, because just one move is needed to move one disk from one pole to the other, so M1, the minimum number of moves to move a tower of one disk from one pole to the other is 1. So this is the recursion relationship, and that is the initial condition for the Tower of Hanoi. But now what we're going to do is we're going to try to find a closed form for that. Not a recursion relationship, but solve it so there's a closed form answer. So here is a computation of the next 5 moves. So we got 1 and 2, so M2 is going to be 2M plus 1, and that's going to be, this is 3, and you see you get where we're using this and we're just iterating on this, and we get this number. Now, if we go back to the legend, suppose the priest worked rapidly, and the question we were trying to answer, and every disk was moved in 1 second. Then the time from the beginning of creation to the end of the world would have been M64. Now in the next section we'll derive an explicit formula for Mn, but for now we can estimate this either using a calculator or by continuing this process, and you should try one of those. But the approximate result is this ends up being this many seconds, which is this many years, which is this many billion years. And we're talking about 60 seconds per minute, 60 minutes per hour, hours per day, and this is the number of days including leap years in a year, so that's the seconds in a year. Kind of cool and a very big number. Now, we're going to talk about finding an explicit formula for this. So recall that the Tower of Hanoi, M1, M2, Mk of that example, satisfies the recurrence relation this, because we already verified this, and has the initial condition M1 is 1. So we can start iterating. So we have this, we have this, we have this. Now notice that when the subscript is 2, k is 2, we get a 2 there. And when k is 3, we get a 1 there, excuse me. When k is 3, we get a 2 there. When k is 4, we get a 3 there. Okay, but notice that we're getting these additional terms. So M5 is going to be this. So we start with 2 to the 4th plus 2 cubed plus 2 squared plus 2 plus 1. Now that tells us that this is what we are going to be finding. For example, M6 is going to be this. It's going to be 2 times that plus 1. But if I distribute that 2, then it's going to be 2 to the 5th plus 2 to the 4th plus 2 cubed plus 2 squared plus 2 plus 1. And so in general, this is what we would have. M sub n is 2 to the n minus 1 plus 2 to the n minus 2 all the way down to 1. But you see that is a geometric series, and we know the sum of the geometric series is 2 to the n minus 1 over 2 minus 1. But 2 minus 1 is 1, so that is just 2 to the n minus 1. So the explicit formula seems to be m sub n is equal to 2 to the n minus 1 for every integer n greater than or equal to 1. Let's prove that answer using induction. You see that we didn't prove it really there. Now we're going to prove it using induction on n. Okay, so we will start, and this is our predicate function. It is p of n, and that means that m sub n is equal to 2 to the n minus 1. So we start at 1. So we have to say P of 1 is true. Well, so we must show that M1 is equal to 2 to the 1 minus 1. So the left-hand side of that is M1 is equal to 1, and the right-hand side is also 1. Therefore, we've shown it's true for 1. Now we have to show for every integer k greater than or equal to 1, if P of k is true, then P of k plus 1 is also true. So here's our induction hypothesis. We're going to say that mk is equal to 2k minus 1, and we must show that this is true. P of k plus 1 is true. But let's start with the left-hand side then. This is equal to this by the definition of these. But that's equal to 2 times mk plus 1. And so there's the 2. Now we're using the induction hypothesis, plus 1. And we're distributing the 2, and we get this. But that is going to be 2 to the k plus 1 minus 2 plus 1 is 2 to the k plus 1 minus 1. That's algebra, and that is the right-hand side of pk plus 1. So we have proven this by induction that that is the correct formula. That's a good review looking ahead towards the final exam. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. May God bless you all.